So I'm going to talk about surfaces, how you build them, how you classify them. Then I'm going to talk about surfaces with geometry. What does it mean for a surface to have some geometry? And I will concentrate mainly on a hyperbolic geometry. What does it mean for a surface to be hyperbolic? And then that's going to take at least half of the talk. And then I will move to something more specific to Maryam's work, to Mizakhani's work. The first one is counting curves on surfaces, and the other one is going to be about the space of all surfaces. Let's start with something very elementary. So what is a surface? So of course, the basic example is that of a plane. But we are topologists for this first half of an hour. And we will be allowed to deform the plane. So surface for us is going to be something, actually a topological space, that locally looks like a plane. For instance, this sort of a hat is going to be a surface for us. So the first thing I will try to do is to explain that surfaces are built out of elementary pieces. So when you start with a surface, I'm going to explain a process that will transform the surface into elementary blocks. So how do you do that? You do that by cutting your surface into smaller pieces. So let's explain the process. The first thing you need to consider are an essential simple curves. So what does this word mean? So you know what a curve is. So simple means that you don't have any self-intersection. That's a definition of being simple. So this curve does not have self-intersection. This one has. So this one is not simple. Then the other condition is of being essential. Non-essential, it's easier to define, is when your surface bound a disk. And this one is essential because it doesn't bound the disk. So when you have done that, you can repeat the process. So you can find another essential simple curve. So here you need to add some extra condition. So you want that your second curve here does not intersect the previous one. Okay, and the other condition, which is a little bit like to be essential, is the fact that you don't want this curve to be deformed into this one. So this is a curve which is different from this one in a topological sense. It cannot be deformed into this one. So let's repeat the process. So you see that there is another essential simple curve here, which is not like the previous one and does not intersect them. And then you can repeat the process again, and you can repeat it. And there is one more curve that you can draw, which is this one. So here, and that's something that you have to show, the process actually finished. There is no more essential simple curve that you can draw on your surface. So let's consider what happens now if you cut your surface along these curves. So I'm just going to use coloring to have different sort of to explain what are the different pieces. So you have 1, 2, 3, 4 different pieces. And if you cut along these pieces, you see that your pieces actually look all about the same. And they are what we call a pair of pens. Do a further operation, which is to cut this pair of pens into more elementary pieces. So what you do is just you consider because if you are someone who wants to make a pair of pens, you cannot actually obtain that. You need to have flat pieces. So what you do is you make a sewing. So you have this curve here, and this curve here. And if you cut along these curves, you obtain 2 hexagons. So now we have a complete description of how to build a surface. You start with many hexagons, and then you glue them together to get a pair of pens. Then you glue again the pair of pens together to get a closed surface. So on the basic result of a surface topology is to say that every closed, connected, oriented surface is exactly being obtained by this procedure. So first, you have actually for the Euclidean plane, you also have a boundary at infinity. So what is a boundary at infinity? There is an extra relation between lines, which is to be asymptotic. So your object is going to be, or at a parallel distance. So your boundary at infinity is going to be the space of lines up to this relation of equivalence. So one property, which is very important in hyperbolic geometry, is that given 2 points at infinity, you can join this by a geodesic. From that, you obtain some very important property, which is that in hyperbolic geometry, there exist infinite triangles. So now you are able to prove your result that any sort of the surfaces built out of pair of pens, that means excluding the torus on the sphere, they can be equipped with a hyperbolic geometry. So you start with this right angle, you glue them back, exactly how we did for the torus, and we obtain a pair of pens, which is hyperbolic. Then a surface, you glue back the pair of pens, and you obtain a surface, which is hyperbolic. So what do I mean here by hyperbolic? It means that locally, any small ball in this space is going to look like a small ball in hyperbolic plane. The spectrum is that you can associate to every primitive closed geodesics, you associate it's just length. Okay? So one of the basic results, the number of closed geodesic of lengths smaller than L is finite. Maryam did, and it's going to be a special case of a more general result, which I will try to explain, that if you take a hyperbolic surface, then the number of simple closed curve is asymptotic to L to the 3p times V of sigma. So what is P here? It's an integer number, which is precisely the number of pair of pens that you use to build your surface sigma. And the other thing here is something which depends only on the Euler characteristic, of course, for the experts. And this constant V of sigma, I'm not going to say more than that. So let's now be a little more precise about the space that we are going to be interested in. So the first one is Riemann moduli space. So Riemann moduli space is a space of hyperbolic surfaces with p-pens divided up to isometries. We said that two hyperbolic surfaces are the same whenever they're isometric. So this is a pretty complicated space, and you may want to fix an extra data. And one extra data is this decomposition into pair of pens. So here you see that the corresponding object, hyperbolic surfaces with p pens with a fixed decomposition of pair of pens. Now that's exactly as we said, it's r to the 3p over 2. So we have the length, which are parameters, and then you have this twisting parameter, which look like S1. So this object is exactly going to be that. What people actually prefer is the cover of this one, universal cover of this one, and this corresponds to not only fixing a pair of pens, but what is you fix one decomposition pair of pens, and you fix extra curves, which are blue in this picture here, and this what is left are hexagons. So now this object really is r to the 3p, and this object is called Teichner space. And the relation between these two objects is given by the mapping class group. So formally, the mapping class group is given by the space of homomorphism of the space of connected components of homomorphism of sigma preserving the orientation. What is the result of Maryam Mizakhani now? I'm sorry, this is not very friendly. It's again you want to count the number of a simple closed curve in an orbit of the mapping class group. So you start with a curve gamma, 0, and you applied your mapping class group to it. So you have infinitely many simple curves generated by the process, for instance, I explained for the length twist. And now you want to count just the number of those curves gamma whose length is less than L. And the result is that, again, this is asymptotic when L goes to infinity, to L to the 3p, V of sigma, the same constant as before. But now, of course, this depends on the curve gamma 0 that you start from. So you have a constant which depends on the topology of your curve.